Today we're going to continue simplifying radical expressions. Today's problems involve division.
So let's say we wanted to simplify the expression the square root of 11 divided by the square root of 49. 11 does not have any perfect square factors, so we would leave it as the square root of 11. However, we can simplify the square root of 49 to 7, and so we would do that. And we would be done simplifying that expression. So here we have the square root of the quantity of 25 divided by b to the fourth power. Now the property that we just mentioned says that we can separate these out, and we could think about this as the square root of 25 divided by the square root of b to the fourth power. Now when we do that, we end up with two perfect squares. So we can simplify each part of this expression by taking the square root of those perfect squares. Let's look at this expression. So we have the square root of 144 divided by 9. Now right away you probably recognize that both 144 and 9 are perfect squares. So we could simplify this by separating out the numerator and the denominator, and then finding the square root of each. So we would find the square root of 144 is 12, square root of 9 is 3, and now we have 12 divided by 3, which would give us a quantity of 4. What if, though, we wanted to divide first? We could do that. So 144 divided by 9 happens to be 16. So we could write that as the square root of 16, which is a perfect square, and simplifies to 4. So again, if you want to divide first, you can, or you can simplify and then divide. So look at this expression. We have the square root of the quantity of 25p to the third divided by q squared. I would probably tend to separate by putting the quantity of the square root of 25p to the third divided by the square root of q squared. We have perfect squares that we can factor out. We're left with a p on top and a q on the bottom. So the 25, the square root is 5. P to the third, we could take out the square root of p squared, which would give us p, and we're left with the square root of p still, and we can take the square root of the denominator. The square root of q squared is q. Now here's an example of a problem you would definitely want to divide before you simplified, because if you divide this, then you know you're looking really for the square root of 8. The square root of 8 can be simplified to the square root of 4 times the square root of 2, and the square root of 4 is 2, so we're left with 2 times the quantity of the square root of 2. So I want you to think about this one before you start doing anything, and hopefully you'll see that there is some simplifying that could happen here. If you have a to the third divided by a, you know you could simplify 1a away, so you end up with a squared in the top with no a's on the bottom. 12 and 7 have a common factor of 3. So if you divide both of them by 3, now we're really looking for the square root of 4a squared divided by 9. Lots of perfect squares left here. So we could say the square root of 4 is 2, the square root of a squared is a, the square root of 9 is 3. If we hadn't simplified first, that would have been a much more complex problem to solve. In this example, 90 is not a perfect square and 5 is not a perfect square. So I suppose we could try to simplify 90 by factoring it to 9 times 10 divided by 5. We know that 9 is a perfect square, so we could take out the square root of 9, and we're left with then 10 in the numerator, 5 in the denominator. 10 divided by 5 is 2. That is one way you could do that problem. Oops. Another way to do that problem is just to divide 90 by 5, which would give you 18. The square root of 18 could be thought of as the square root of 9 times the square root of 2. And then you could find the square root of 9, which is 3, and then times the square root of 2. Two different ways to do the same problem. Okay, so when we simplify radical expressions, we never want to keep a radical symbol in the denominator. That is just one of those rules. So the way that we get rid of it is by a process called rationalizing the denominator. And the way we do that is we need to get rid of the denominator, the radical in the denominator. So we can multiply this expression by a form of 1 that would include a radical. Now think about what we just did. All we did was multiply. This is like an equivalent fraction, but we're using a form of 1 that includes radical symbols. So it's simple to see the top would be, 2 times the square root of 5. And when you have the square root of 5 times the square root of 5 in the denominator, you get 5. Because that would be like saying 5 times 5 is 25. The square root of 25 is 5. So now we have a simplified expression that has no radical in the denominator. So this process we're talking about, rationalizing the denominator. We do this whenever the denominator is not a perfect square. So we rationalize it in order to get rid of the radical symbol. And rationalizing means you're multiplying by a form of 1 using a radical. All right. In this expression, you can see that we have a radical in the denominator. So we want to turn the denominator into a perfect square. Now, we could multiply it by itself, but we could also multiply it by anything that would turn it into a perfect square. So watch. What if we multiply the form of 1 as the square root of 2n divided by the square root of 2n? Now, why would we do that? Because now, look at our denominator becomes the square root of 16n squared, which is a perfect square. Our numerator becomes the square root of 14n. So now we can't do anything with the numerator, but the denominator we can simplify. The square root of 16 is 4. The square root of n squared is n. So here's an expression with a radical in the denominator that we need to get rid of. We can always multiply by itself, right? Because anything times itself would be a perfect square. So what do we have when we do this? Well, we end up with the numerator of 3 times the square root of 3. And the denominator, square root of 3 times square root of 3 would be 3. Now, you might notice that we could take away a 3 from both the numerator and denominator, and make this just the square root of 3. Okay, here's another expression that contains a radical in the denominator. So our goal is to make it a perfect square so that we can remove the radical. So I could multiply this by the square root of 18t. However, that's going to give us some bigger numbers to have to deal with in the numerator. So I'm going to, instead of doing that, I want to multiply this by something that's going to give me maybe the smallest perfect square that I can find. And I recognize that 18 is a factor of 36, which happens to be a perfect square. So I'm going to multiply both the numerator and denominator by the square root of 2t. So now we have the square root of 36t squared in the denominator. And in the numerator, we have the square root of 10t. So now we can simplify. I think the numerator is in its simplest form, but now we can take the square root of 36, which is 6, the square root of t squared, which is t. Okay, our last example, the square root of 7m divided by 10. Now, you might say, well, it's already in its simplest form, but you have to remember that law or the property of square roots with division says that we need to rewrite this as a division problem. And now we do have a radical that we need to deal with in the denominator. So I think I would just tend to multiply this by the square root of 10 divided by the square root of 10. So now we have the square root of 70m divided by the square root of 10 times the square root of 10 is 10. And I don't believe there is a perfect square factor in the number 70, so that would tell us that we are in our simplest form right now.
So in summary, a radical expression is in its simplest form when all three statements are true. The radicand has no perfect square factors other than 1, the radicand has no fractions, and the denominator has no radical.